Adding an SPI-based LCD panel to your Raspberry Pi Pico using MicroPython opens up a vast array of possibilities for your projects. So let me show you just how quick and easy it is to get up and running. Hi and welcome to Bytes and Bits. You can pick up one of these little SPI-based LCD panels very cheaply on Amazon or eBay, and they're great for creating a user interface for your project or for creating a small gaming console. And connecting them to your MicroPython enabled Raspberry Pi Pico is actually quite a straightforward project. You only require 6 connections, and thanks to some great MicroPython libraries, driving the display is just as simple. So in this tutorial, I'm going to show you how to connect the LCD panel, how to add the library software to your project, and then how to use some primitive shapes and so on like line tools and so on. So let's get started with the actual circuit. The Raspberry Pi Pico offers a wide array of interfaces to allow you to connect to various devices. Our LCD panel uses an SPI interface, so you will need to use one of the 2 hardware SPI channels. We can use software to allow us to turn any GPIO pins into an SPI channel, but doing it that way runs much slower and uses up much more processing power than the hardware drivers. If we look at the Raspberry Pi Pico pinout diagram, we'll see that the SPI 0 and SPI 1 interfaces can be set to use a number of different pins. So our first design decision is to decide which configuration we're going to use for our SPI connections. So I'm going to use SPI channel 0, and I'm going to connect that using GP16, 17, 18 and 19. If we then look at our LCD panel, we'll see the following connection pins that we need to connect to. So in our setup, our Raspberry Pi Pico is termed the master device and the LCD panel is the slave. So MOSI stands for master out slave in. So this signal needs to connect to the data transmit pin on the Raspberry Pi. MESO, or master in slave out, needs to connect to the data receive pin on our Pi. SCK, or the serial clock signal, that provides the pulses that move the individual bits of data across the channel. CS is the chip select signal, which allows us to tell the LCD panel when we want to talk to it. DC is the data command pin, which we'll use to tell the LCD panel if we are sending it a command instruction or some actual data. Reset allows us to send a hardware reset signal to the panel, and LED pin is the power supply for the screen backlight. On top of these, we obviously need to connect 0 volts to ground and 3.3 volts to VCC. Now you can use 5 volts for the positive supply, but as all the signals that we're going to be using from our Pi Pico are at 3.3 volts, we may as well just use that to keep everything the same. So from this list of connections, you'll notice that our standard SPI connection on the Pi Pico doesn't include the DC and reset pins. So I'm going to use GP15 for my DC signal and GP14 for the reset. So this gives us this following circuit diagram for connecting the SPI LCD panel to our Raspberry Pi Pico. And you can find all of these circuits and code examples and so on the main project page on my bytesandbits.co.uk website, and I'll put links to that in the description down below. So now that we have these connections made, all we need to do is to find a way of driving the LCD panel from our software. Now there are a number of MicroPython packages that we can use, and I'll actually be making a video after this one where I'll take you through the whole process of creating your own driver package. So please do make sure that you subscribe to my channel so you don't miss this next tutorial. But the package that I'm going to use for this video can be found at this web address. Now this is a really good library package which also includes a driver for the touchscreen module, but we're not actually going to be using that in this video. So to use the package, we simply need to download the files and save them into a folder on our development machine. So on the GitHub repository page, click the green code button and then download a zip archive of all the files. Then extract these into a folder for your project, and then we can open this as a new project in PyCharm. Now once you open it in PyCharm, don't forget to go to the project settings and enable MicroPython support, and then let it load in the required packages. If you're not sure how to set up PyCharm, then please do watch my setup video for programming your Pi Pico, and I'll put links to that in the description down below. Now the repository does contain a number of files and folders which we don't need for our project, so we can clean up our project folder to only keep the code and asset files. So now we need to get our panel up and running. And the really good feature of this library is that it has a great selection of demo programs. So let's try a couple of these to make sure that we've got everything connected correctly and that our Raspberry Pi Pico is able to drive the display. So if we start with the demo bouncing boxes .py file, we can see the code required to get the LCD panel set up and under our software control. So looking through the listing, the program starts by importing all the packages that we're going to need. The standard machine library includes a hardware SPI driver, which we need to import along with the pin library that lets us control our GP pins. We then need a few functions from the random library and the microtime library, but the main one we are interested in is the ILI9341 library, and that provides the support for our display. And inside that, we'll import the display object and the color565 function. So the ILI9341 is the driver chip used inside the LCD panel that I'm using. And there are a number of different ILI93 series driver chips, depending on the LCD's panel resolution, but they all use the same basic set of commands. And actually quite a few other manufacturers for these LCD driver chips use this same common command set. So you should find that this driver is able to control most of the SPI LCD panels that you find. The display class that we are importing contains all the code to not only handle communication with the LCD panel, but also many primitive shape drawing functions that we can use to put things on the screen. The color565 function that we're using is used to translate RGB color values from the normal 24-bit or 3-byte resolution into a 16-bit or 2-byte resolution. And now within this 16-byte number, we use 5 bits for our red value, 6 bits for our green value, and 5 bits for our blue value, hence the name for the 565 color. Now the code mainly consists of a box class, which simply models the coloured rectangles that are going to be bouncing around the screen. But the important bit for us in this class is the draw method, which we can see uses this display class's fillHrec method, and that simply draws a coloured rectangle on the screen. Now you'll see that this draw method actually draws 2 rectangles one after the other. And that's because anything that we draw on the screen just simply stays on the screen until we remove it. So to animate a rectangle moving, we have to first remove the previous rendering of the rectangle, and that's what this first hrec call does, and that draws the rectangle in a background colour, which in effect just erases it. And then after that, we calculate the new position for our rectangle and then draw it in its proper colour. So that gives us our animation frames. So moving down the listing, we then come to our test procedure, and this is the main entry point that contains the program loop. Now it starts off by setting up our SPI interface using this built-in SPI hardware library. Now the code contained in the display driver library example is actually designed for a different circuit board, an ESP32 board, so we do need to modify this slightly to get it to work on the Raspberry Pi Pico. Now the constructor function for the SPI class takes a number of parameters. The first parameter is the hardware SPI channel that we want to use, and as we saw earlier, I'm planning on using channel 0. The next parameter sets the baud rate for our SPI channel, and this is the value in hertz. So we'll start this one with a 10 megahertz clock signal, and that's just to make sure that we are well inside the operating specification for both the Pico and the LCD panel. The next parameter that we need to specify is the polarity, which tells the SPI channel what voltage level to set the clock signal to when we're in our standby mode and we're not sending data. And usually this will be high, so we specify this as a 1. The phase parameter is next, and this tells the SPI channel whether it needs to sample the data on the first edge or the second edge of our clock signal. The bits parameter then sets the number of bits per data value, and the first bit parameter tells the interface in which order our multiple byte data should be sent. So our LCD panel expects the data to be sent in big endian format, and that means that when we have a multiple byte value, and we're going to be using some 16-bit values, which of course take up 2 bytes, then we need to send the most significant byte first. So after that, we tell the SPI channel which GP pins we're going to be using for our clock, MOSI and MISO signals. And if you have a look in the example code, you'll also see that the author doesn't actually specify a MISO pin. And in this demo, we're never actually going to be sending data back from the LCD panel to the Pico. So in reality, the signal isn't really needed, but I always think it's a good idea to connect it up for any future reference. Now, once we've got the SPI channel initialized, the code then instantiates an object of the display class, supplying it with a reference to this SPI channel, and then telling it which pins we're using for these other data signals. We then define an array of available colors using the color565 function to convert RGB values into these 16-bit values that the screen understands, an array of box sizes, and then we create the actual array of box objects which are going to be animated on the screen. The main program loop simply moves each of the boxes, calling its draw method to display the animation, and then has a short delay at the end to keep the code running at 30 frames per second. So we've now got everything in place to give the panel a test. Now, if we look at the project structure, we can see that we're now using a number of different files, some of which might be contained within separate folders. So to get the software to run, we need to make sure that all the files used by our code are uploaded into the Raspberry Pi Pico. Now, we can either do this manually, copying each file one by one, or if we have a larger project, we can actually tell PyCharm how we've structured our project and get it to do everything for us. Now, I know in this particular demo program, we only need to have the bouncing boxes .py file and the ILI9341 driver file. But we can, just as to show you how it's done, we can get it to upload the complete project up to our Pi Pico. So if you go to the File menu and open the Project Settings, underneath the Project dropdown, you'll see the Project Structure option. And clicking on that will bring up a list of the folders used by our code. On the right hand side, you'll see the main list detailing the project root folder and then any source folders and excluded folders. So at the moment, the VENV folder is marked as excluded, as this is the one that contains the virtual environment used by our project when running on the main PC. The fonts and images folders contain source code and assets that are used by other demos in the main LCD driver package. So if you right-click on one of these, you can mark it as a source folder so that PyCharm knows that the files in this folder need to be transferred to the Pico. If you then do this for the other folder, we've got our project set up to allow PyCharm to manage our project uploading. So if you apply those changes and then go back to your project, we should be able to right-click on our project root folder and then flash the entire project to our Raspberry Pi Pico. As we're flashing the entire project in one go, this may take a while as there are a few bitmap images in the images folder. But once we've got everything uploaded, we only need to update any files that we change, which will make the process a whole lot faster. So now that we've got all of the files uploaded, we'll need to run the bouncing box demo. Now by default, the Pi Pico will try to run a file called main.py once we upload our project. But because we don't have one in this demo system, it will just sit there doing nothing. So to run the code, we need to actually log on to the REPL interface for the Pico and then start the code manually. So the REPL interface is basically a console app that runs inside the Raspberry Pi Pico when it's using MicroPython. And it lets you talk directly to the MicroPython operating system so that we can see what's happening on the Pico, as well as asking it to perform various operations for us. So in PyCharm, you need to go to the Tools menu, MicroPython, and then select the REPL link. And this will start the Python REPL console and leave you with a prompt where we can start typing our commands. Now to get the code to run, we simply need to import the file into our runtime environment and the demo will start to run. So type import demo_bouncing_box, and we don't need the .py. It's just like you're importing a library file at the top of your program listing. So the screen should then start up and we should now start seeing bouncing boxes bouncing around. So if everything is working, then that's great. If not, check your wiring and that you have the correct pins defined in the demo code. And if you need to make any changes to the code, do make sure you re-upload your demo file then to get that working. Now, when you're using the REPL console in PyCharm, you must close the window before you can actually upload any of your files. So the basic rule is that you can only have one communication link with your Pico open at any one time. And you'll also find that the backspace key in this REPL console, it worked a bit strangely in that when you press it, it is actually deleting the characters, but unfortunately for every character that it deletes, it actually adds a couple of extra ones in, so you end up with this garbled message. They're not actually typed in, these extra characters, but it does make it very hard to see what you've currently got in the console. So I find if I do make a mistake on the line, the easiest way is to either just backspace to make sure the whole thing's gone, and then press the return key, and then I can try typing in a blank line again. Now the LCD driver has most of the basic drawing functions that you'll need to build your project. And these include rectangles, lines, circles, text, and even using bitmap images. Now each of these functions is demonstrated in one of the demo programs, so do have a look through those to see how each of them works. And you can also look through the actual library source code to see how each of these functions has been implemented. If you do want to run the other demos, don't forget to update the SPI class constructor call parameters to the Raspberry Pi Pico version. You should then be able to upload that demo file and start it from the REPL command line. If you do use one of the image-based demos, such as the sprite demo, you should already have the image folder uploaded if you followed through my instructions earlier on. But if nothing shows up or if you get an error in the console, then do make sure that these files have been added to the Pico and that they are inside the images folder. So that should give you enough information to get your SPI LCD screen attached to your Raspberry Pi Pico so that you can create some great user interfaces or start coding some games. There are, however, a number of drawbacks to the way in which our system works at the moment. So when you draw objects on the screen, you need to overwrite them to change them. And this involves blanking out the current image before you draw the new one. And each of these drawing operations needs the Raspberry Pi Pico to communicate with the LCD screen and to send data across. Now, because we're using a serial SPI channel, any data transfers will be limited by the baud rate of the interface. Now, as we saw in the constructor function for the SPI object, we can set the baud rate, but the maximum the Raspberry Pi Pico can manage is about 31 MHz. Now, although this is quite a fast transmission rate, when we have a lot of larger objects being animated on the screen, it can cause the whole system to slow down, especially as the core processor has to wait for the SPI channel data to be sent before it can continue with your application code. So in my next tutorial, we'll start to look at how we can optimize this code and create a bitmap display that uses a frame buffer to allow us to use frame-by-frame animation techniques rather than this overdraw technique. So please do make sure that you subscribe to my channel and like my videos, and then you can get hold of that video as soon as I publish it. So I hope you found this introduction to using an SPI LCD screen with your Raspberry Pi Pico useful. I look forward to seeing you in another video very soon, and bye for now.
For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.